Previously, I gave an overview of the Anova test, which looks at comparing the means of more than two groups. And the way in which it does that is to compare the between group variability to the within group variability. Now I'd like to give you a few details about the formulas that are used within Anova. So I'm going to start with some notation. The first bit is that I is going to be the number of groups. Then n sub I is going to be the number of observations within a group. So we saw with our smoking example that there were 200 individuals in most of the groups, but the non-inhaling group only had 50. N dot is going to be the total number of observations. So I can add up all of the observations from each group. Y sub I bar is going to be the mean for group I. And then S sub I will be the standard deviation for group I. And so you figure that I can find the mean and the standard deviation for each of the groups, and then that information is going to be helpful in doing my comparisons. So I want to start with looking at the deviation of an individual observation from the overall mean. So y sub ij is the jth observation in the ith group. Okay, so that's just an individual observation in a particular group. And I want to see how that deviates, okay, from the overall mean. Well, one way to look at it is to take that observation y sub ij and then subtract its group mean, because that compares that observation to its group mean and how far away it is from its group mean. But then I'm going to add to it y sub I bar again. That'll cancel out the previous y sub I bar minus y sub double bar. Okay, so what I've written there compares each group mean to the overall mean. And since I added and subtracted the group mean, I've essentially added 0 to this expression, so I haven't really changed it. So this gives me how far an individual observation is from the overall mean by thinking about how far it is from the group mean, and then how far the group mean is from the overall mean. Now what I'm going to do with this is I'm going to square both sides. And I'm going to square both sides so that I can create something that looks like a variance. Okay, so if I square both sides, I want you to notice that there are two pieces that I'm going to be squaring. There's this piece and this piece. And I'll refer to them as A and B. Okay, and I want to square them. Okay, well, how do you square them? Well, if you write it out as a product, you would get a squared plus b squared plus 2ab. Now, I'm sure you were thinking the 2ab would be in the middle because you're used to doing, say, a FOIL method where you do first, outer, inner, last. Okay, but I thought I would change that up a little bit and do what I call the FLIO method, which is first, last. That's the a squared plus the b squared, and then the inner and the outer add to 2ab. Okay, so what I'm going to do is I'm going to square the right-hand side and then sum over all observations in all groups. Okay, so I'm going to have to write down a sum from I equals 1 to capital I, which is the sum over all groups, and then a sum from j equals 1 to m sub I, that's the sum over all observations. Okay, and then the first part squared will be y sub ij minus y sub I bar squared. Okay, and then I'm going to keep writing these sums down. So the sum from I equals 1 to capital I, sum from j equals 1 to n sub I, so that's first the groups, then the individuals within the groups, and I'm going to sum y sub I bar minus y double bar squared. Okay, so that's the a squared and the b squared, and then now I'm going to have 2ab, so that's 2 times the sum from I equals 1 to capital I, that's the sum of the groups. Sum from j equals 1 to n sub I, that's the sum over individuals within the group. And then I have yij minus y double bar times y, sorry, that's not minus y double bar, that's going to be minus the group mean, y sub I bar, and then I have y sub I bar minus y double bar. Okay, I've written all that out, and that looks a heck of a lot more complicated, but it turns out there's a simplification. So when I look at this last term, the 2 times that sum of a times b, it turns out that when you sum all of these things up, you end up getting 0. Seems kind of miraculous, okay, but it turns out that there must be some sort of kind of Pythagorean theorem thing going on where these two things a and b are perpendicular to each other. So it turns out that whole sum goes to 0, which is pretty awesome. Okay, so that leaves me with the other 2 sums, and I'm going to give them names. I'm going to call the first one the sum of squares within, and then I'm going to call the second one the sum of squares between. And so what we've created is, first on the left-hand side, the total sum of squares, which measures the overall deviation of the data from the mean. Okay, so every single data point, I subtracted the overall mean, okay, and then I squared it, and then I added them all up. Okay, but then what's on the right side is composed of 2 parts. Okay, the sum of squares within is a sum over all the groups, and then the sum over all the data. And what am I comparing? I'm comparing each individual data point to its own group mean. So that's the deviation of each data point to its group mean, and I'm summing that squared. So that makes a sum of squares within. Now it turns out we can rewrite this as just the sum over the groups, and then we can recognize that what's on the inside here looks like a variance. We took the data point, subtracted the mean, and squared it. It looks like a variance. The only thing that seems to be missing is if I had divided by n minus 1. So what I really have is then is n minus 1 times the variance, which is s sub I squared in our notation. So that really simplifies it down. Okay, so I have n minus 1 times the variance. And I'm summing that up. Okay, now I have the sum of squares between, so that's the sum from I equals 1 to capital I, summing over all the groups. And then I'm going to sum from j equals 1 to m sub I, each group mean minus the overall mean. So I'm measuring between the groups, the group mean and the difference between that group mean to the overall mean, and I'm squaring it, right? So that's why it's the sum of squares between. Now it turns out that this can be simplified as well. So I can still have the sum over all the groups, okay? But now what you see here on the inside does not depend on j. Okay, so I'm summing over j, but it doesn't depend on j. And so it's a constant, okay, for each individual I. So what I'm going to get is if I sum the same number, n sub I times, I'm just going to get n sub I times that number. So again, I can simplify that down to one sum, the sum of n sub I, okay, and then times the difference between the group mean and the overall mean squared. Now it turns out that there are degrees of freedom associated with both within each group and between each group, okay? And so the degrees of freedom within is going to be the total number of points minus the number of groups. If you think about it, that's essentially adding n1 minus 1, and then n2 minus 2, 1, and then n3 minus 1. You're adding that up for all the groups. So you're adding the degrees of freedom for all the groups, okay? And so that's basically the sum of the degrees of freedoms for the groups, okay? And then what is the degrees of freedom between? Well, I have I groups, okay, that I'm comparing. And then so if I'm going for degrees of freedom between the groups, that's going to be capital I minus 1. Okay, so using that information, we're going to define the mean square within and between groups. Okay, so the mean square within is going to be the sum of squares within divided by the degrees of freedom within. And then the mean square between groups is going to be the sum of squares between divided by the degrees of freedom between. Okay, so let me say what each of those are going to be. Okay, so this mean square within is going to be the sum from I equals 1 to capital I. I am now realizing that I made a mistake way back here, okay, where I was summing over all the groups, so that's capital I. And then that's going to be n sub I minus 1 times s of I squared over n dot minus I. And what this really is this is a weighted average of variances. Average of group variances. Okay, because I have my group variances that are the s of I squareds, okay? And then I'm multiplying them by the sample sizes minus 1. And so I'm adding all those up and then dividing by the sum of those sample sizes minus 1. Okay, so that's a weighted average of group variances. And that makes sense as our kind of mean square for within the groups. The sum of squares, or sorry, the mean square between the groups. Okay, I'm going to sum from I equals 1 to I. And then for between, I'm going to have n sub I times y sub I bar minus y double bar squared. And then I'm going to divide that by I minus 1. And then this is going to be a weighted average of what I'm going to put in quotes because it's not exactly, but it's going to be a variances of the sample means. Okay, because we're comparing each sample mean to the overall mean, and so this is a weighted average of the variances of the sample means. And so now it's those two pieces, the within group mean square and the between groups mean square, that I want to compare with my Anova test. Okay, because what we want to see is that between group variability, if it is much larger than within group variability, we will be able to reject our null hypothesis. So let's go ahead and look at what the test will look like then. So we're going to recall that the hypothesis for our test is that all the means are equal. Okay, that's the null hypothesis, that all the group means are equal. And remember, these are the population means, not the sample means. Okay, and then our alternative hypothesis is that at least one mean is different from all of the others. Okay, so I think I wrote the mu sub i's are not all equal, but what I mean here is at least one population mean or one group mean, I guess is the way I'm going to write it. One group mean is different from the others. Okay. And our basic idea is that we're going to reject the null hypothesis if between group variability, is sufficiently larger than within group variability, like I showed with the pictures in the previous video. Okay, so how are we going to compare between group variability to within group variability? Well, we're going to define what's called the F statistic, and that's going to be a ratio between the two. So I'm going to take the mean square between, and then I'm going to divide it by the mean square within. So that ratio tells me how large is the between group variability compared to within group variability. If mean square variability is much greater than, if mean square between is much greater than mean square within, then the F statistic will be large. Okay, so, and if my F statistic is large, the groups are going to be very clearly distinguished. Okay, as having different means. Okay, so if the variance between the groups, or the variability between the groups, is much bigger than the variability within the groups, okay, I'm going to get that a large test statistic. It's going to tell me that I have clearly distinguished groups. But if the mean square between groups is much less than the mean square within, then my F statistic will be small, and the means will be difficult to distinguish statistically. Okay, so therefore, if our F statistic is sufficiently large, we're going to reject the null hypothesis, because a large test statistic tells us that our groups are clearly distinguished. Okay, so why is this called the F statistic? Well, it turns out that geneticist R.A. Fisher was responsible for developing the F distribution. Okay, so I said before that the T distribution is for comparing means. The chi-square distribution is what you would use to compare variances. The F distribution is what you would use to compare the ratios of variances. Okay, and it has two parameters. Okay, those two parameters are going to be the numerator degrees of freedom, which is going to be the number of groups minus 1, and the denominator degrees of freedom, which is going to be the total number of observations minus I. So the numerator is for between, and the denominator is for within. Okay, so based on those two parameters, you will have an F distribution. You can see it kind of looks like the chi-square distribution, at least in terms of its shape. Okay, that the top 5%, right, is maybe defined by a number f.05 with two different degrees of freedom, saying that the area above that is going to be 5%. Okay, and if our F statistic falls in this area, we're going to reject the null hypothesis. But if it falls down here, we're going to say we're unable to reject the null hypothesis. So when I do an example, I'll show you the F distribution from table 10. Okay. But essentially, if our F statistic is bigger than our F for our alpha, say for 0.05, we're going to reject the null hypothesis and conclude that at least one mean differs from the others. And so that concludes how we can put together the formulas for the Anova test and how we're going to conduct the Anova test using the F distribution. I'll do an example in the next video.